In the first part of Notes 13, everybody took a sample of 30 cane toads, and now we're going to answer some questions about what you saw and what it might mean when we think about everybody's different samples that they took. So again, if you haven't done that yet, pause the video real quick, check your minute hand, and try to see what the minute hand is and use that to find your sample of 30 cane toads and figure out what number of them are female, and go back to the first page to see how you would calculate the proportion that are female. So we're going to use these two graphs here on the next page. This graph is a histogram of 60 sample proportions from the cane toad population. So as if we had maybe our class, everybody do this twice and write out their sample proportion. This graph represents 10,000 sample proportions. So, maybe if we did this over and over and over and over and over again. All right. So the first thing I want us to think about is, based on the graph of sample proportions for the 60 samples of 30 cane toads, what do we think is the most plausible value for the true proportion of female cane toads in this population? And so we could look at this graph and we could say, well, the very lowest that anybody got was about 20% of the cane toads were female, and the very highest that they got, it looks like, is around 60%. And if you sort of look at how these are spread out, you probably notice that 40%, or a sample proportion of 0.4, is right in the middle here, and that seems to be kind of the most common thing that's occurring. And so you would probably imagine that if 40% of the cane toads in the population were female, then we would tend to get sample proportions that were also sort of around that value. Some would be smaller, some would be higher, but they'd be kind of in that general area. And so based on this graph, I would probably say that the most plausible value for the population proportion of cane toads that are female is somewhere around 0.4. All right? So now I want you to think about, well, what does that mean for the sake of taking samples from this population? So let's say we had two different biologists that reported their results. They each claimed to have gathered a sample of 30 cane toads, and after they reported their results to us, someone told us that, you know what, I have reason to believe that one of those biologists actually didn't go out and get their sample, they just stayed at home, they made up a number, but the other one, they definitely did take a sample. And maybe you ask them, okay, well, which biologist was it? And they say, sorry, I don't know, I didn't get a name or anything. I just know that one of them faked their data. And we might say, okay, well, let's look at their results and see if we can try to guess like which one is real and which one is fake. So there's two options here. Biologist A got a sample proportion of 0.63. Biologist B got a sample proportion of 0.4. And you can already see here that I've filled in that we would probably come to the conclusion that this first biologist is the one that faked their data. And if you had to sort of stop and think about, well, why might that be? You'd look back up at this graph and you'd see, well, a lot of biologists that actually did go out and take their samples, they got results right around sample proportions of 0.4. Now, a sample proportion of 0.63, it looks like maybe that's not impossible, but it's pretty unusual. It doesn't seem to happen very often if somebody actually goes out and finds their data here. And so we might use the graph to reach some sort of conclusion like that. We would say, you know what, it's pretty rare for someone to actually gather the data and get a sample proportion of 0.63. Getting a sample proportion of 0.4, on the other hand, is pretty common. So if I had to, guess which one of these two people faked the results, I'm probably going to lean towards the one that gave me a result that seems pretty strange. All right? And we might follow that up and say, well, this person told us that one of the people faked the data, but I don't know who this person is. Like, maybe they're the one that's lying. So is it possible that both of these results are real? Like, both of these biologists really did go out and gather random samples? And again, you can see that I've filled in that, yes, it is possible. But you might want to stop and think for a second, well, why am I saying that's possible? Or what kind of results would be possible? And if you think about it, say, well, I guess technically it's possible that my entire sample could be female cane toads. I said that there's thousands and thousands of cane toads in this population. and I'm randomly selecting 30 of them. So as long as more than 30 out of those several thousand are female, it's possible that I could get all female cane toads in my sample. So any proportion is technically possible. On the other hand, if I go back up to this graph where I said that I took 10,000 samples from this population, you can see that even though things like that are possible, it seems like maybe there's like one really, really tiny bar somewhere over here with a proportion of like 70% or 80%, but it's so incredibly uncommon. And I definitely didn't get anything where 100% were female or 0% or anything like that. So we can start to see that there's a difference between what's sort of theoretically possible versus what's actually probable and maybe like actually going to occur here. All right. So one more question. Each person in our class collected only one sample. How might we be able to use that single sample to accurately estimate the population proportion through something like a confidence interval? And you might think about how the graphs on the previous page could help us understand this process. So maybe you want to pause the video real quick and try to see if you can think about this and figure it out on your own for how you might do that. But I'll give you one explanation right here. Now, if I scroll up to this graph here, now I'm saying that we're only taking one sample. So I've got 10,000 samples that I'm looking at, but in reality, you don't know what 10,000 samples look like. You know what your sample looks like. However, it's possible that I can start to get a sense of how spread out my different samples would be. All right, so even if I don't know exactly where this graph is centered, I don't know if it's centered near 0.4 or 0.6 or 0.8 or something like that, I might be able to start to understand that if I were to take a bunch of samples from a population, a graph like this would get produced. And if that's the case, and let's say I realize that, well, when I do take samples of 30 cane toads or students or Americans or apples or whatever it is that I'm talking about, the sample proportions in those samples kind of look like they're maybe, in this case, from about 0.2 to 0.6, which tells me that most of the time, my sample proportion is probably within about 0.2 of the population proportion, if I assume the population proportion is somewhere in the middle here. So I don't know exactly what the population proportion is, but I've got a sense of how close most sample proportions are. So essentially what we can learn from this process is that in certain situations, I may know that my sample proportion is pretty likely to be within some amount, let's say 0.2 from the population proportion. And that tells me that I can take my sample proportion, which is my best guess for the population proportion, and then I can give myself a little bit of room on either side of that, maybe 0.2 above it and 0.2 below it. And essentially what I'm describing is a confidence interval. And so we can use a similar process to what we've used for population means to create confidence intervals in a situation like this. All right? So a little bit later in the notes, I'll share the actual true proportion of female cane toads. But for now, even with your sample, you can probably start to come up with a guess. You can start to figure out, well, it's probably around this, and most people are getting sample proportions that are, within about 0.2 or so of that number. And so you might have an idea for the range that this population proportion is in. And again, there's thousands and thousands of cane toads. You looked at 30 of them, and you're already getting some information about that whole population. So this is where statistics is really helpful to us. The biologist doesn't have to go and try to capture, 10,000 cane toads. They can maybe capture 30 and learn some information from that that will help them understand the population better.